As no one has joined till now, I will wait for 10 minutes and we will start the um, presentation by 6:10 p.m. Good evening, everyone. Welcome to the week 7 of Biomass Conversion and Biorefinery. The course coordinator for this course is Professor Costa Mohanty from the Department of Chemical Engineering, IIT Guwahati. And today, I, Arihan Oja, a PhD scholar in the Department of Paper Technology, IIT Roorkee, I am your TA for this course. Currently, I am working under the Professor Vibhor Kumar Rastogi, who is in Department of Paper Technology, IIT Roorkee. So today we will discuss about the week 7 assignment of 2023, and then we will move on to the week 8 preparatory questions so that you can solve your week 8 questionnaire. So let's start with assignment 7 2023, which we have solved, which you have solved in this last week only, and we will discuss here that what were the answer of these and what was the reason behind it. So let's move on to the first question. The molecular weight of vegetable oils can be calculated by iodine value, saponification, both A and B, or none of the above. So the answer for this is saponification value. Saponification value tells us about the molecular weight of oils. It tells about the molecular weight. And the iodine value is not the right answer because it tells about how many double bonds are there. It just tells us about the how many double bonds are there, and saponification is the right answer. So, what is these iodine value and saponification value? We will discuss it now. So, the iodine value and saponification value of a vegetable oil can provide information about its chemical properties. Iodine value is a measure of degree of unsaturation. So, iodine value tells us about the degree of unsaturation. So, it tells about the number of double bonds present in the fatty acid chain. And the higher the iodine value, higher the degree of unsaturation. So the if the iodine value is higher, the number of double bonds present in it are higher. This is because iodine reacts with double bond in fatty acids. So the more the iodine reacts, the more are the double bond. So therefore, the higher the iodine value, higher the unsaturation of the fat of your vegetable oils. But on the other hand, saponification value gives us idea about the molecular weight of the fatty acids in oil, and it's totally different than iodine value. Saponification value, if it is higher, then the molecular weight is lower. So it's opposite to iodine value because iodine value, if iodine value is higher, we will get higher amount of double bonds, and if the saponification value is higher, the molecular weight is lower. This is because saponification process, the fatty acid chains are broken into smaller components such as glycerol and soaps, and the amount of alkali for this reaction is directly proportional to the molecular weight of the fatty acids. So now let's move on to the second question. The most commonly employed alkaline catalyst for transesterification is. So before moving to the answer, what is transesterification reaction? So uh, transesterification reaction in this case means that if we have a oil, the oil is in triglyceride form. So these triglycerides, with the presence of any type of alcohol and some catalyst, are used to convert it into glycerol and fatty acid methyl esters, also known as fuel. This is your biofuel. So this is known as transesterification. To convert your triglycerides, which are oils, triglycerides are nothing but oils, and with the help of alcohol and a catalyst. So the question is, what type of catalyst are required? So all of these can be used, but sodium and potassium hydroxide are only generally employed. Rest are not employed because lithium and magnesium hydroxides are not so much available, and their reactivity is also low. So the most commonly used are sodium and potassium hydroxides. So transesterification reaction is a reaction in which triglycerides derived from vegetable oils, these are vegetable oil only, are reacted with alcohols, usually methanol or ethanol, in the presence of a catalyst. And what are these catalysts? These are potassium hydroxide or sodium hydroxide. And they produce fatty acid alkyl esters, which are known as biodiesels. The process involves breaking apart the triglyceride molecule into the constituent fatty acids and alcohol components and then reassembling them to form the ester molecules. And this is a very most commonly used method by the industries, and it is it can be performed on a very large scale also. So, and it's a very conventional method to produce biodiesels. So this is the most common method, and sodium hydroxide and potassium hydroxides are the most common catalyst we used for the transesterification of oils to produce biodiesels. So this is a typical reaction in which you can see it is a triglyceride which is oil, and we use alcohol in this case. And if the catalyst can be KOH or NaOH, and this catalyst helps the alcohol to break down this chain, and breaking this chain makes it convert into glycerol. And then we get is these types of esters, which are fatty acid methyl esters, and this is known as biodiesel or biofuel. And so we can get biodiesels from the oil, or particularly triglycerides. So, sodium and potassium hydroxides are the most commonly used alkaline catalyst for transesterification reaction because they are highly basic and reactive. Additionally, they are readily available and relatively inexpensive. But on the other hand, such as lithium and magnesium hydroxide, these are also alkaline but not commonly used because they are more expensive and less readily available, and they are not as effective as potassium hydroxide and sodium hydroxide. And if we use lithium hydroxide or magnesium hydroxide, we might need a activator for them also, so we do not use them. Now let's move on to the third question. The aromatic acid content in canola oil should not exceed. So first of all, what is this aromatic acid? So aromatic acids are nothing but these are C22 1. It means that it has 22 carbon chains, and one double bond is present there. So this is a type of fatty acid with 22 carbon chain and one double bond. So it is a type of unsaturated fatty acid, and it is present in canola oil in very high percentage. But due to some reasons, due to some health issues by aromatic acid, only some amount is restricted in canola oil. So some type of purification is done so that aromatic acid is um, made below the permissible level. So earlier it was 5%, but now only 2% is the requirement by some European and US countries. This is because that this particular acid is not good for heart, and it is responsible for many heart diseases. So therefore, the aromatic acid is controlled under the 2%, under the 2% in the canola oil. So, aromatic is a monosaturated omega-9 fatty acid denoted as C22 1. We know now that it means 22 carbon chain and one double bond. And the aromatic acid should not exceed 2%. This is because aromatic acid has been linked to heart issues in animals and humans, and there are some regulations. So, food grade canola oil is regulated to maximum of 2% of acetic acid by weight in US and 2% in EU. But earlier it was 5%. Therefore, the NPTL has the answer 5%, but now it is 2% only. So, now let's move on to the fourth question. The advantages of inorganic membrane over polymeric membrane for biodiesel purification are, so first of all, what is this membranes? So when we create a biodiesel, it has many kind of impurities. So to purify them, we pass it through some kind of membrane, and this membrane contains some types of adsorbents, and it's a porous membrane also. So the biodiesel can be passed through it, and it might have some impurities in it, which will get stuck here, which will get absorbed here, and we will get purified biodiesel. So there are two types of membrane which we can use to purify the biodiesel. First is polymeric membrane, and second is inorganic membranes. So polymeric membranes are mostly made up of polymer, as the name has, and inorganic membranes are mostly made up of ceramics or metal. So the question was, what are the advantages of these ceramic or metal-based membrane over polymeric? Are they cheap? Do they have long-term durability, or they are brittle, or all of them? Yes, these are brittle, but it's not a disadvantage. It is a disadvantage, so it's not the right answer. And polymers are cheaper than these ceramics and metals. Therefore, cheap is not also the right answer. The right answer for this is long-term durability. Inorganic membranes are a type of membranes used in separation processes, s- such as in biodiesel, that are made up of inorganic membranes are like ceramic or metals. And these are different from polymeric membranes, because polymeric membranes are made up of organic material, and membranes are made up of inorganic materials such as ceramics and metals. The main difference between these are its structure and properties. Inorganic membranes are rigid. We know that they are made of ceramics and metals, and ceramics or metals are very rigid structures. They are better resistant to heat, acid, or harsh chemicals, and they also have a very longer lifespan when compared to polymeric membrane, which makes them cost effective in long term. But these are not very cost effective when to fabricate it. But when we look at the overall cycle, it is cost effective when looking at the overall cycle. So here are some of the advantages and disadvantages of inorganic membranes. So the advantages are long-term stability of high temperature, because ceramics can withstand very high temperature, and also resistant to high harsh temperatures, resistance to pressure drops, microbial degradation, easy cleaning, and catalytic adhesion. But the capital costs required are very high, and there's a major problem which is known as embrittlement phenomena. Also, the low membrane surface area, difficulty of achieving high selectivity, low permeability, and module sealing at high temperature are the major disadvantages also. And when we look at the polymeric membrane and ceramic membrane, the advantages of polymer over the ceramic membranes do not swell. These are resistant to most of these solvents, but polymers membranes can swell. These can be swell easily, and there is a possibility of uniform molecular sized pores allowing for molecule sieving. And polymeric membranes do not have uniform molecular sized pores. These have uneven pores. And ceramic are chemically resistant and thermally stable, and polymerics are not that stable. But on the other hand, ceramic membranes are higher in cost when produced and more brittle, and polymeric membranes are lower cost and less brittle. So both of them have their own advantages and disadvantages, and thus we can use them according to our needs or our application. Now let's move on to the fifth question. Lipids are in general soluble in. So first of all, what are lipids? Lipids are nothing but type of oil. And what are oil? Oil are non-polar in nature. So now if we go to the question, lipids are generally soluble in non-polar, polar, both, or none of the above. So there's a theory that like dissolve like dissolve like. So non-polar compounds will be soluble in non-polar solvents. Therefore, the correct answer is non-polar solvents. However, some polar solvents can also be used to dissolve, such as ethanol, but at very low solubility. Very low solubility. So some polar solvents can also be used to dissolve these oil, but generally non-polars are used because most of the non-polar can dissolve them, such as toluene, xylene, hexane, octane. There are many numerous non-polar solvents which can dissolve these oils. But polar, we have a very limited solvent such as ethanol, and that too at very low concentration. So as the question was generally soluble, so the correct answer is non-polar solvents. So lipids are generally soluble in non-polar solvents because they are themselves non-polar or hydrophobic in nature. Non-polar solvents such as hexane, chloroform, and ether have a similar, so they are effective in dissolving or extracting lipids also. While lipids are generally considered more soluble in non-polar solvents, sorry, while they are considered more soluble in non-polar solvents, as we have seen, they can also be soluble in polar solvents such as ethanol. However, they are typically less solvent when compared to non-polar solvent. So we have seen that non-polar solvents are generally used to dissolve lipids, and there is a simple solubility test which we can perform, and this is how it will look if we mix oil in any non-polar solvent. It will be homogeneously mixed, and on the other hand, if we use any polar solvent such as water, we will get a layer of oil and water, and they will not mix. So this is a way in which we can see that if oils are soluble in non-polar solvents or in polar solvents such as water. So now let's move on to the next question. So as the cetane number increases, the ignition delay. So the correct answer for this is that the ignition delay will decrease. So the cetane number, if is it is high, so the ignition will be more faster. Ignition will be faster. Therefore, the delay will decrease. So, what is this cetane? So, cetane is a hydrocarbon compound found in diesel fuel. So this is particularly used for diesel fuel, and it is used as a measure of the ignition quality of the diesel fuel. And the cetane number is also a type of rating given to a diesel fuel or how quickly it can ignite. The higher the cetane number, the shorter the ignition delay, and therefore higher cetane number diesel fuel will ignite more quickly, completely leading to better engine performance. So here also we can see that if the cetane number is increasing, the we get a very fast burning. And on the other hand, there is another number known as octane number, which is used for gasolines. And if the octane number is higher, it means that it will be slow burning. So octane number and cetane number, there are two things which we can define, and octane numbers are usually mostly used for gasoline, and cetane number is used for diesel. So octane number is a measure of performance of a fuel, while cetane number is a measure of delay of the ignition of a fuel. And octane number is important for predicting the knocking of the engine, while the cetane is used for the predicting of the ignition of engine. And octane numbers are used for gasoline, as we have discussed here also, and cetane number is used for diesels. While octane rating is done considering the octane number is of isooctane is 100, cetane is done considering the ignition of cetane we consider in it. So there's a very simple method and simple formula to calculate the cetane number in this, and the formula is that in this, if the T2 is the ignition delay of the test fuel which we are testing, and the T1 is the ignition delay of the alpha methylene reference fuel, and the cetane number of this fuel is usually 0, and the T3 is the ignition delay of the cetane reference, which has the value of 100. So this is how a cetane number of any test fuel T2 can be calculated. Now let's move on to the seventh question. If a fatty acid is represented by C18-1, what does it indicate? So C18 means it has a carbon chain of 18. So there will be 18 such carbons, and 1 means that among these 18, only one will have a double bond. So, and at last, all these have COH. So that's why it is known as fatty acid chain. So the correct answer is 18 carbon atom and one double bond. And this is a typical fatty acid chain. If we look at this, it how many carbons are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it can be represented with C10 because there are 0 double bonds and 10 carbons. On the other hand, this has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this will represent a C10 because it has one double bond. But what if it has a one more double bond here? So we will write it as C10 2. So I hope now you know what is saturated fatty acid and unsaturated fatty acid and how do we write in short form. So now let's move on to the next question. The most important criteria that needs to be considered for adsorbent selection is, so first of all, what is this adsorbent? Adsorbent are some kind of material which are used to dissolve the impurities present anywhere. So let most of the adsorbent are carbon. So these carbon should have some kind of attraction towards the impurities such that these impurities go on the surface and stick on the surface. So this is known as adsorption by an adsorbent. So what property should it have? Selectivity, adsorption loading, regenerativity, or all of them? So the correct answer is all of the above. So it should be selective. For example, if we have a fuel with some impurities, and if this adsorbent is not selective, so it can also adsorb some type of fuel also, which is not required because we only need impurities to be adsorbed. So there should be a selectivity for the impurities. So therefore, the answer is impurity selectivity. Also, how much impurity can it take? Can it per surface area? So adsorption loading is defined by that. How much adsorption can a material can adsorb? And finally, the main thing is regenerability. Let's say that we have a carbon with lots of impurities. We have used it fully. It is fully uh, filled with the impurities. Now we can recycle this and reuse it again so that we can get an pure adsorbent. So this is known as regenerability. So in order to reuse the adsorbent material, so therefore all of the above are the right answer. All of them are major requirements when selecting a good adsorbent material. So this is what our adsorbent looks like, and these are the impurities which get stuck to the adsorbent. And this is not a chemical phenomenon, but these are mostly physical um, bonding between them. So adsorbent is a material that is used to remove impurities or abnormality coming from mixture by selectively absorbing the desired substance onto its surface. So now we have seen that why selectivity is important. So the adsorbent should be preferentially adsorb the target molecules over the other molecules. Second, why adsorption is loading is important because the amount of target molecules that can be adsorbed per unit weight of adsorbent is also our main criteria. Thirdly, regenerability, the ability to adsorb to be regenerated, to use multiple times, to reuse it again and again, is known as regenerability. And there are two more other things, that are stability and cost. So stability, that it should not break down or deteriorate during the regeneration process, and cost, that it should be reasonable or affordable for specific applications. So these are the major requirements which we look for the adsorbent selectivity for the purification process. Now the next question is, which mechanism has been proposed for potassium prompted iron catalyst in FTS? So it follows the mechanism of semi-strong back donation. It might seem complicated here. I will explain this thing in the next slide. Before going to the mechanism, what is FTS? So FTS is a Fischer-Tropsch synthesis, and it is a reaction to convert carbon monoxides and hydrogen to liquid hydrocarbons. The major thing is to make them, which can be used as a fuel. So this reaction is typically carried out using a catalyst, which speed up the reaction and produce desired products. So in FTS, potassium prompted iron catalysts are used, and in this, these work through a process known as semi-strong back donation. So this means that iron atoms in the catalyst are able to share electrons with carbon. So these, in this potassium prompted iron catalyst, the iron atoms share the molecules with the carbon monoxide and H2 to help them break down. And potassium act as an activation for this catalyst. So this is known as semi-strong back donation mechanism. So the role of potassium in this process is to activate the iron. So potassium is activating the iron, and this iron catalyst is to make iron effective at breaking down the carbon and hydrogen molecules. So potassium does this by interacting with the iron atoms in the catalyst, which help to increase the catalyst activity and selectivity. So this is known as semi-strong back donation mechanism, which helps to increase the efficiency and effectiveness of the reaction. And now let's move on to the last question of assignment 7. The major fatty acid in soybean oils are. So soybean oil is a very highly unsaturated fatty oil, and unsaturated fatty oils means the presence of double bond. So among these, C18-1 and C18-2 are the two most found fatty acids in soybean oil. What are the C18 and C18-2? C18-1 are the oleic acid, C18-2 are the linoleic acid. So therefore, the correct answer is oleic acid and linoleic acid. So this is the typical um, composition of soybean oil. Here we can see that oleic acid and linoleic acid collectively makes around 76% of the uh, total soybean oil. Now we will discuss about the week 8 preparatory questions. We will discuss some of the questions which are related to your week 8 questionnaire, and it will help you to solve the questions. So let's start it. The relation between equivalence ratio and gasification temperature is. So before going to the answer, let's discuss what is equivalence ratio. So equivalence ratio, ER, indicates fuel lean mixture. A value less than 1 of equivalence ratio means fuel lean mixture, and if the value is very greater than 1, it means fuel rich mixture. So if equivalence ratio is less than 1, it means fuel is less than air, and if ER is greater than 1, fuel is higher in quantity when compared to air. So Fueling refers to a situation in which there is a lower amount of fuel being used, being fed to the combustion system related to the amount of air or oxygen. So if we increase the ER, it means that we are increasing the fuel, and so fuel to oxygen is being fed to more, which will facilitate the formation of micropores and increase the surface area of the biochar. However, more oxygen can also cause biochar to become weaker and result in lower rate. Therefore, if we increase the equivalency ratio, it will lead to gasification temperature. Therefore, the answer was directly proportional. Now, let's move on to the second question. The devolatilization process results in which of physiochemical properties of the biomass? So, first of all, what is this devolatilization? If you look at the word, it means that to remove the volatile compounds. So, devolatilization. So to remove these volatile compounds is known as devolatilization. So what will this do? What will it affect the physiochemical properties of biomass? So first we will understand what is devolatilization more. It is a process in which volatile compounds in a substance such as biomass, coal are released. So in when we consider biomass conversion, devolatilization refers to thermal degradation of biomass in absence of oxygen, leading to release of volatile organics such as water, methanol, acetic acid. So we will just heat the biomass, and some volatiles will be removed from it. So this is known as devolatilization. So in this process, what it results is in biochar. So this is a process to convert biomass to biochar. So this remaining biochar is carbon-rich material and can be used for soil amendment also, and it is a key step in the production of fuels such as pyrolysis oil, which is obtained by heating. So now we come to the question: the devolatile results in increase of what? So we have seen that devolatilization converts biomass to biochar, which is a carbon rich source. Therefore, the correct answer is fixed carbon content. It will lead to increase of fixed carbon content. So, during devolatilization, volatile compounds such as water, organic compounds, gases are released from the biomass, leaving behind the solid residue. So, we burn the biomass, and it will such that our gases or volatiles or waters will get released and leave behind a solid residue. So this solid residue is mainly of fixed carbon and ash. Therefore, the fixed carbon content of the biomass increases as a result of devolatilization process. What is a typical yield of the bio oil that can be obtained using rotating cone reactor? In previous lectures, also we have seen that a rotating cone reactor biomass is fed with sand and heated sand, and this is done so that the biomass present in it gets heated very evenly. So this evenly heating by sand in the rotating cone indicator leads to very high yield. The yield is very much higher. Therefore, it results in 60 to 70% of bio oil. So a rotating cone reactor is a type of pyrolysis that has been shown to have high yield of bio oil. And in this also we can see that if we pour hot sand and biomass and the rotation, both of these combined makes yield very higher. It operates at very high temperature and pressure, which allows for efficient conversion of biomass to liquid fuel. Additionally, the reactor design helps to promote good mixing and heat transfer between the biomass and the gas, which further enhances the conversion process. Now let's move on to the next question. The effect of addition of solvent in bio oil is. So we know that what is a bio oil? Bio oil is a very viscous type of oil. It is a very viscous oil, and what happens is when it gets aged, if we store it for a longer time, Then during aging, some chemical reaction takes place, and these chemical reaction makes it more thicker and more thicker, and at a time it becomes a very solid product, which is not oil now. So this is known as aging of bio oil. This aging can be prevented by just one thing, and that is by the using of solvent. If we use the solvent to dissolve the bio oil, then this aging has stopped. Therefore, the correct answer is decrease. The effect of addition of bio oil is decrease the aging of the bio oil. So, bio-oil is a complex mixture of oxygenated hydrocarbons produced during fast pyrolysis, and it has very highly reactive components such as acids, aldehyde, ketones, and water, which can cause the reactions such as oxidation, polymerization, and condensation. Therefore, aging will lead to increase in viscosity, acidity, solid content. Therefore, bit after the aging, the stability of the oil will be less. So this is a typical type of oil. So here also can see that this oil is now solidified and is not liquid anymore, and further it's not also dropping below. So bio oil solidifies with aging due to some internal chemical reaction happening inside them, and this aging can be stopped with the help of solvents. So the addition of solvent to bio oil can decrease the rate of aging of the bio oil. This is because aging of bio oil is primarily caused by the presence of reactive functional groups in the bio oil, such as carboxylic acid, aldehydes, and ketones. These reactive groups can further undergo further reactions such as condensation and polymerization, which can result in formation of larger compound. So if we add some solvents in the bio oil, the reaction in the bio oil will stop or happen at a very low rate. So the aging is not stopped, but the aging decreases with time if the solvent is present in it. Now let's move on to the next question. What is the optimum temperature required to produce biochar that is useful in the increasing the fertility of the soil? So we know that if we make biochar in the range of 750 to 900 degrees Celsius, we get a very high quality of biochar. We get a very high quality of biochar. So this high quality of biochar can be used to increase the fertility of the soil because it is higher quality. So therefore the answer above is above 170. But sometimes this high temperature also makes some chemical changes in the biochar, and might this might not be useful also. So 500 to 600 degrees Celsius is also used. So higher temperature allows for the efficient removal of volatile matter and other impurities from the biomass while preserving the structure. Therefore, higher the temperature, higher the quality. But sometimes temperature of 750 may lead to biochar having a lower surface area and certain contain fewer functional groups, which can make it less effective. So sometimes 500 to 600 degrees Celsius is also employed in order to retain the high surface area and minimize the functional group present in it. Now let's move on to the next question. What are the optimum process parameters to be maintained to obtain a higher energy density of torrefied biochar? So before going to the answer of it, we'll discuss what is this torrefied or torrefication process. So torrefication is a thermal process that involves partial carbonization of the biomass in the range of 200 degrees Celsius to 300 degrees Celsius. So this involves it means that if we heat the biomass but at a temperature of 200 to 300 only, what we do is we are doing carbonization of this, which is similar to the toasting of bread. So the process is similar to roasting coffee beans or toasting a bread. So the objective of torrefication is to improve the quality of the feedstock and making it easier or handled and increase the energy density. So before processing this biomass, we first purify it in order to increase the quality. So this process reduces the moisture content, volatile matter, oxygen content of biomass, and increase the carbon content and make it more energy dense. The resulting product is torrefied biomass. So this biomass is torrefied to produce torrefied biomass, which is very high quality, and this can be a feedstock for biofuels in order to get high yield of biofuels. So generally, a biomass at 100 degrees Celsius, we can remove the moisture. But some volatiles and tars cannot be removed at 100 degrees Celsius. So we do torrefication, that is 200 to 300 degrees Celsius. So in this, volatiles and tars can be removed. And then this purified biomass can be used to produce biofuels. So, what are the optimum process parameters to be maintained to obtain a high energy density of purified biochar? Now we can say that higher purification temperature, higher residence time are required to obtain high density purified biochar. So, a higher purification temperature and longer residence time leads to result in higher energy density of biochar, and this is because at higher temperature, more volatile compounds can be driven off, leaving behind more carbon-rich material. So, now let's move on to the next question. Which of the following is true for biofuels? Presence of water enhances the calorific value, enhances the corrosion, or has declining effect on the growth of microorganisms. So we know that water promotes corrosion. So this is the right answer. And if we see the microorganisms grow only where there is water. So this is not the right answer because water has a good effect in the growth of microorganisms. It promotes the growth of microorganisms. Also, oil fuels have high calorific value, but if there is water present in it, it doesn't have a good calorific value. Therefore, the correct answer is presence of water enhances the corrosion. So, presence of water. Now we have seen that presence of water in biofuels has a negative effect on the calorific value, and as it reduces the energy content by diluting the fuel. So this is a particular table that shows how water affects the calorific value, and if a typical fuel has a calorific value 1781 kilocalorie per kg, then within 10% increase in water content, the calorific value decreases. So as the content of water increases, the calorific value decreases. Also, we know that corrosion is mostly caused by the water. We know we have seen this in our daily lives also. And microbial habitat is favored by water. Where there is water, microbes will grow over it, such as fungus, yeast, molds, bacteria. All of these grow near water only. So the correct answer for this was that water acts as a corrosion for the process. Now let's move on to the next question. Which of the following method is used to determine water content in the fuel? So the correct answer for this is Carl Fisher and Fourier transform infrared. Therefore, the answer is both A and B. So Carl Fisher titration is the oldest process, and it's a type of destructive process because it uses fuel to determine the water. Whereas FTIR is an old process, is but it is a newly used nowadays, and it is a non-destructive method. So only a drop of oil will be used to analyze this. So FTIR are now being more applied nowadays due to its non-destructive and requirement of very less oil. So Carl Fisher titration is a quantitative method to determine the water content in oil and is a widely used technique in petrochemical, pharmaceutical, and environmental studies, and it's based on the reaction of water with iodine and sulfur dioxide. So higher the iodine requirement, higher the water content it will have. So it's a typical titration method. Whereas FTIR is a different method. It is a kind of spectroscopy. In this, what is does that we place a drop of liquid over the diamond crystal, and infrared rays are passed through the oils. So during this infrared rays, the compounds or the polar groups inside them, they get excited and they vibrate or stretch. These vibrate or stretch or do so these molecules emit different uh, amount of energies at different wavelength. So we can make a graph of absorbance or transmittance, which is energy, and wave number, which is the inverse of wavelength. And by the intensity of these uh, peaks, we can identify how much groups are present in it. So this is a typical spectrum of pure biodiesel, and generally water is seen at 3500 and 1650 peak. So here we can see this is the peak, and there is one more here. So there are no peaks here. Why? Because it is a pure biodiesel and it has no water in it. But if we look at this one, this is the impure. So if we look here, sorry. So if we look here, so the bottom graph is plain, and as the water increases, it becomes more bumpier. So this broad area here in the 3600 to 3200 range is shows the amount of hydroxyls, and H2O also has a hydroxyl. So therefore, higher the amount of H2O, higher the intensity of this peak. Also, there is one more peak here. You can see this is caused by 1640 or 1650, and it denotes the absorbed moisture present in the sample. So in the bottom graph, the red, we see that there is no peak, which is in the case of pure fuel. But as the water increases, this peak gets increasing. Therefore, with the help of these two peaks, we can determine how much water is present in the FTIR. And it is a very fast process also. It just takes few seconds to complete the test. Just we have to analyze the height and intensity of this absorbance of these two particular peaks to determine how much water is present in it. So now let's move on to the next question. Using the hot vapor filtration, the ash content can be reduced up to. So before going towards the answer, we will discuss what is hot vapor filtration. So hot vapor filtration is a biomass gasification technology that can reduce ash content in the product gas. The process involves passing the hot product gas through a filter made of refractory such as ceramic. So in this, a raw gas is fed to this system. This system has some kind of ceramic layers which has some kinds of adsorbent also. So this raw gas passes through this, and the impurities are stuck in it by physical phenomena, and we get what is known as clean gas. So this process involves passing the hot product gas through a filter made up of refractory materials such as ceramic, and the filter traps the ash particles and allow clean gas. So ash can be trapped inside these ceramic filters. So now, using the hot evaporation, the ash content can be reduced up to. So the ash content can be reduced up to 0.01% because it is a very effective process, and it adsorbs all most of the ash content from the um, our product. gas. Now let's move on to the next question. At what temperature the probability of occurrence of secondary condensation reaction can happen? So first of all, what are these secondary condensation reactions? First we will discuss about this, then we will come back to the question. So it is believed that during pyrolysis, that at temperature below 400 degrees, some secondary condensation reaction occur and the average molecular weight of the liquid product decreases. And these secondary reaction may occur in liquid phase, leading to further decomposition polymer condensation reaction. These secondary reaction can cause changes in molecular weights, in particular temperatures below 400 degrees Celsius. So these secondary reactions are not uh, good things which we require. These are unwanted reactions. So these unwanted reactions occur below 400 degrees Celsius only. So we usually apply a higher temperature for pyrolysis to avoid the secondary condensation reactions. So that's all for today, and I hope that you have learned something new about the week 8 assignment, and you might also have understood some basic concept and which will help you to solve this week's questionnaire. And if there is any problem or if you want to ask any question related to the assignment 8, feel free to contact me. I'm writing my email address in the chat box. You can contact me anytime. I will be very happy to assist you. So thank you for listening, and we will meet you next week.